Good morning, guys. Good morning. How's it going? I hope online is treating you well. Guys, this week we're going to learn about a very special number called e. But I've decided before we do that, we'll have a whole lesson about logarithms. Now, what I remember, logarithms you learn early in grade 12, so you probably haven't got into it. I don't think you do it in grade 11. And you need some kind of understanding of logarithm. So I've decided to have a whole lesson on logarithms. Also, I think it will help you in core maths because, again, from what I remember, I don't know how maybe in your higher set is different, but we don't spend enough time on logarithms in core maths because it's not as essential. But it actually is important. So this lesson will help you obviously in AP, but also in core maths. Where is this core logarithm, concept of logarithm comes? So it all comes from inverse function. You've got a whole chapter on inverse functions. So if I look at, let's say, y equal x plus 2, okay? What is a function? A function is in math, you call it a map. It's a fancy word. It's a map, okay? That takes any number from a set that we call domain, call it D, okay? So there's a whole bunch of x's there, yeah? And for each one of these, it gives one. It has to give only one, otherwise it's not a function. It gives it one value of y in a whole set of numbers that we call the range, okay? It can't give more than one answer, otherwise it's not a function, okay? So y equal x plus 2, for example, if you take x equal 1, then the y equivalent is 3. So we'll give an example. So the number 1 will be mapped into the number 3. Now, one would then maybe ask himself, if there's a map that goes from here to there, maybe it's the reverse map. And the answer is, if it is a function, well, normally there is, yes, there is a map, a reverse map. We call it the inverse function. So you know, sometime y equal x plus 2, you can write it as f of x equal x plus 2. Okay? So if that's the function, the reverse function, okay, will be called f minus 1 of x. Okay? It really will take, for example, if we put a 3 there, then the answer will be 1. Okay? And one of the things you're going to do in core maths, and I'm not going to get into too much because you'll have enough time to do that, is to determine the inverse function. In fact, what am I talking about? We've done it a lot in AP last year. So if I want to know what the inverse function of that, remember what we've done. We first of all we swap the letters. So we say, okay, x equal y plus 2. And then we're trying to find out again what is y. So y will be x minus 2. Okay? So the inverse function of this will be f minus x, x minus 2. Okay? Alright? Y equal, then I didn't make a mistake there, right? Yeah, x minus 2. Okay? Which kind of makes sense. Here we're adding 2, and the inverse will just take it away that 2. You'll get to where you got. Okay? I'll pause here for a second. Okay, so this stuff actually we did last year. What we didn't do is look at the inverse function of an exponent. You know exponent from, I think at least from last year in core maths, okay? Exponents, it can either blow up, it can either go down, or it can land or go like that, okay? I will, at this point, just deal with the one simple case. I'll leave you to do the rest in core maths, okay? So y equal ax, where really, when I drew it like that, I really said, I assume that a is larger than 1. Right? If a is larger than 1, it blows up. If a is smaller than 1, or between 0 and 1, it will go down like this. If a is negative and smaller than minus 1, it's going to flop like that. And if a is between minus 1 and 0, it's going to go like that. You will deal with all these things in core maths. So the question is, right, if this is the function, f of x equal a over x, I can ask myself, what's the inverse function? Okay? What's the inverse function? Okay? Now, you might say, okay, let's just do the same thing. So y equal a power x, and then we'll swap the x and the y. X equal a power y. And then I want to find out what is y equal to. And if you take a minute and think about it, you realize actually there's nothing we can do. I mean, how do we get rid of that a and then just make sure the y goes down? Do we divide by a? Do we multiply by a? You can think about it, you can pause me for a second and have a go at it, but trust me guys, there's no way of doing it. Okay, we don't have an algebraic tool to be able to put that y down and put the a somewhere else. Okay, so for that we invented a whole new function, and it's the definition of that function. Okay, so to find what y is equal to, okay, we put that three words, logarithm. We put that little a at the bottom, which we call the base, and x. Okay? Now, that is the definition of a log. Okay? If I go, let's draw it here, okay? If I go from a bunch of x's to a bunch of y's through f of x equal a power x, okay? If this is my function, the exponent function, then if I want to go back to my original x, I need to use an inverse function, which is log of x base a. That will bring me from if I went from, let's say, 1 to 4, and I put 4 here, it will bring me back to 1. Okay, that's the definition of the logarithm. Okay, this thing is called the base. Okay? It's the base of the logarithm. So we can have many different logarithms: base 1, base 10, base 15, base 3. Okay? Many bases, but that is the definition, and that's what you're going to do. Okay. Just a few notation here. If I just, let's say, have log 3, okay, and I don't have any base, if I didn't write anything, then that really means that the base is 10. Okay? I can already mention now, sometime you'll see these letters Ln. Okay? Let's say Ln3. Okay? This is the natural logarithm. Okay? I don't know, in Israel we call it lamb, but I'm not sure exactly how you say it in English. But it's the natural, N for natural, it's a natural logarithm. Okay? And the natural logarithm really means that the base is this special number e, which we hopefully going to learn about later this week. Okay? It's 2.71 whatever. Okay? It's an irrational number. Okay? So again, I'll pause here. This is what we got to remember. Okay, now I want to talk a little bit about graphically. Okay? What do these two equations, y equals log of x and y equals a of x, what do they look like? So I want to go back before deal with a simpler function, y equals 2x. Okay? And I want to ask ourselves, what will be the inverse function? Okay? If you think about it, we've done that last year. Okay? If I'm multiplying something by 2, the inverse function is divided by 2. That will bring me back to my original one. So I'm going to try and draw y equal half x like this. Y equal x over 2. Now what I'm going to do, I'm going to plot a little symmetry line, okay? Or just a line, okay? This line is y equal x, okay? Okay, just a straight line, 45 degrees angle from the orange, okay? Now what you can see, hopefully, is that these two, okay, this is your f of x, and this is your f minus 1 of x, they are symmetrical, isn't it? They're symmetrical. If you fold f of minus x over the symmetry line y equal x, you will get your original function. And that turns out to be the case in every kind of function, okay? There is a way of, like a clever way of proving it. I'm going to leave it now. I just want to demonstrate it with these easy functions. So for example, if I use x equal 1, okay? We'll put x equal 1. Well, y equal 2x will be 2. Okay? Now, if I use 2, if I put that, so if I'm going from from 1, the function will bring me to 2. Well, the definition of the inverse function tells you that it should do the other way around. So if I put a 2, it should give me back my 1, right? So if I put 2 instead of x, yes, indeed, I get a 1. Okay? And again, it's not a proof, okay? But for that to happen, so that if I go from here to there, and then I want to put that back here to get back to there, then you can, I'm convincing you that these two lines must be symmetrical. Okay, they must be symmetrical. Okay? So again, it's not proof. I can prove it. If you really want to send me a message, I will send you a quick video proving it. But that's hopefully just convincing. Okay? Now, that allows me now to draw the graph of y equal log x. Okay? So y equal ax look like that. Y equal log x, what shall we do? Red. Okay? Would look like this. Y equal log x base a. Okay, you can see it's symmetrical. If I fold all this half over across this line, these graphs will coincide. Okay, now a couple of things to see from here. There's an asymptote, right? A horizontal asymptote that never really reached the x-axis. Okay, x needs to be minus infinity for y to be 0. There's an equivalent vertical asymptote. Make that more clear. Okay. There's a vertical asymptote on the log. Okay. It actually never reached the y-axis. Okay. Yeah. So for that reason, by the way, x cannot be negative. You see, there's no negative x's here. X cannot be negative. X must be larger than 0. It's actually never 0 as well. Okay. For x to be 0, y needs to be minus infinity. Okay. The other point that the symmetry is this point. Okay. So we know what is that point. What is the y value here? Okay. Okay. If x is 0, a power 0, y is equal 1. Okay. So if that's 1, and these are two are symmetrical, if this is 1, 0, sorry, 0, 1, this point is 1, 0. Okay. That means if I put, and this is maybe one of the things that I'll write down later, but I'll write now as well. Log 1 base a. The base can be anywhere. It doesn't matter what base it has. A can be anything. It's forever going to be 0. Okay? So, graphical representation. Now we're going to go on to logarithm rules. Okay, so now we're going to develop some laws that will allow you to work with logarithm. Again, you learn them in core maths, but it's not a huge emphasis. So I think it's good that I spent some time here. So the basic principle, and that's the definition of logarithm, is that if y equal a to the power of x, now you want to know what x is, x will be log y base a. And the way I remember, I mean, it's confusing, okay? But the way I remember it, the a base is always the bottom. It's the base in the exponent, the base of the log. Okay? Now, already one result we saw from the graphs, log 1, any base is 0. Now, I want to actually prove it algebraically. Okay? It will give us a little warm-up. Okay? If, let's say, log 1 base a is equal to some kind of b, I want to find out that b. Okay? Well, according to the definition, and that's all you're going to be able to do in logarithm, you're going to move from this way to that way. So if I want to know what 1 is equal to, you see here, I know if I want to know what y is equal, well, y is basically a power x. So if I want to know what 1 is equal, it's going to be a to the power of b. Okay? So to isolate 1, I just need to do a to the power of b. Okay? Now, what was I here? Just a second. Yes. Okay. So now I can figure out what was b, because remember what I want to know is what b is. I knew it should be 0 from just graphs, and I told you a story about them being symmetrical. But now I can prove to you that b must be 0, isn't it? Only a to the power of what will give you 1? 0. So b must be 0. So we prove that first rule. Okay? Let's move. I'll just pause again. Okay, the next bit is, let's say I have a logarithm of a number with the same base. So log a base a. A can be any number. What is that equal to? Again, I've got to use the definition. If I want to know what this a is equal to, isolate it, I need to do a to the power of that question mark. Okay? Now, what is that question mark is? I'm going back to prep. Okay? No x's, no y. A equal a to the power what? Obviously 1. So the answer is 1. Log a base a equal 1. If I have the same number and its base, it will be 1. Okay? Now, let's move on to another one. A log x base a equal what? Okay? So we've got a to the power of the log of xa. Now let's call this one now, we'll call that y. Okay? Now, it's a little bit tricky. Try and follow me. We've got an exponential function and a logarithm inside it. So a to the power of something equal that. Okay? Like this. Y or a to the power of something equal y. Okay? The only difference between these two equations is that the x now is log x base a. So what I can do, okay, I can just say, okay, if I want to find out what is the x, okay, if I want to find out what is the x, like I've done here, I need to move to a logarithm. So log x base a is going to be log, I'm just using this recipe. I'm going from an exponential function to a logarithm. If I want to find out, this is my x. Okay? If I want to find out that, I'm just going to do log y base a. Okay? Get rid of that now. Now let's have a look what I've written here. Okay? I've written log x base a equal log y base a. Now what does that tell me? Can you tell me simply that x equal y? Right? Obviously, if I've got the same base, the same function, then the x and the y must be the same. In other words, a log x base a is equal to x. And that's a very important function. Now, if you think about it, what we're doing here actually makes sense. Okay? First of all, I'm doing the function, a to the power of something. But then I'm doing the inverse function, log of x. So I'm going to get to where I started from. A to the power of log x, or a to the power of something, will send me to a y. And then this log x will send me back to my x. So the answer I get is x, where I started from. Okay, very important. Pause here. Okay, next time we're going to look at what happens when I've got something multiplication inside my logarithm. Okay. So I'm going to find out what is that equal? The logarithm of xy base a. So I'm going to define the following numbers. Okay. First of all, I'm going to say, let's say this number is equal to r, and I want to know what r is. Okay. Okay. So we're going to define the following: log x base a is p. Log y base a, we'll call it q. Okay. Now, from these definitions, the following follows, okay? And that's the key thing. It's always moving from the logarithm to the exponent, okay? If log x is equal p, that means that x equal a power p. That means that y equal a to the power of q. That's the crucial part that you need to understand, okay? Now, where am I now? Okay, now I can feed these guys into here. Can I feed them in? Just a second, or just wait a second. Yeah, it's a good thing I checked. No, don't do that. So now I'm going back to this. Okay. Now, if this is the case, again, let's write down an exponent relationship. Okay. If the log of xy equal r, that means that xy equal a to the power of r. Okay. Now I'm using these two relations to put into the x and y. So this equation tells me really that AP, AQ equal A power R. Okay? But now I know how to deal with exponents. You always want to move the logarithm into the exponents because exponents are easy to work with. Okay, we know what that is. A to the power of P plus Q equal A to the power of R. And then what do? we drop the base, okay? P plus Q equal R, okay? But what is P? That is P. What is Q? That is Q. So what is R? And that is R. So what I'm getting when I'm adding this equation together with the definition of P, Q, and R, I get the following rule, okay? I can see that log xy base A, remember that's your R, okay, is actually equal to P plus Q. What is P? Log x base A plus log y base A, okay? And that's our next rule, okay? If you got a multiplication of in the log, all you can do is just separate them and add them together. Again, let's pause. Okay, the next obvious rule we're going to try and develop is for not x times y, but x divided by y. And it's exactly the same process. So we're going to first define, let's use a different colorful definition, right? So we're going to say log x base A is P. Log y base A is Q, okay? And then we're also going to write, then we're going to write the exponents version. So A power P, or x equal A to the power P, y equal A to the power Q, okay? And now we need to write something about R, okay? R is going to be A to the power of x divided by y, right? R is equal to A to the power of x divided by y. But now we know what is x and y, so we're going to write down A to the power A power P divided by A to the power Q. And we know how to deal with exponents. You see, that's why we always want to move to exponents. We don't want to deal with logarithms. Okay? That's going to be A to the power of A power, I get it right, yeah? P minus Q. Is that right? Just pause here for a second. Okay, it's actually, I've decided to leave it just to show you that, you know, I'm making mistakes a lot as well. Okay, it's getting a bit hectic here. A to the power, A to the power. Obviously, I made a mistake. Can you spot the mistake that I made? Okay, the mistake is here. Okay, all right. If this is the equation, the definition of R, that is certainly wrong. Okay, what I should have written is x divided by y is A to the power of R. Okay. That would be much better. Okay, so I'm actually not going to rub it. I'm just going to cross it to show you that, you know, I'll make some more mistakes. Okay, x divided by y equal A to the power of R. Now I'm going to rewrite it using these two definitions. Okay, so A to the power of P divided by A to the power of Q equal A to the power of R. And that's a little bit more sensible. I don't have A to the power of A to the power. Okay. Right, how are we going to rewrite that? We're going to write A to the power of R equal A to the power of P minus Q, simple rule of exponent, and that means R equal P minus Q. So like we had before, R equal P plus Q, now we're going to get R equal P minus Q. What is R? Logarithm x over y base A. What is P? What is P over here? Log x base A, and what is Q? Minus log y base A. Kind of makes sense, right? If in multiplication we adding, division we minusing. All comes from exponent. Okay, let's move on. Okay, the next rule is actually really easy. Okay, let's say I have a log x power n in base A. Okay, I don't need to use all these techniques that I did before. Okay, all I've got to do is say, okay, what is that? It's log x, base A, x times x times x times x times x, n times. Okay, but now I've got a rule for a logarithm of multiplication. Okay, by the way, okay, I didn't really show that to you, but if I have more than one term, if I have log of x, y, z, then it can easily be shown that it's simply log of x plus log of y plus log of z. So I can generalize it to many multiplications. So now I have many multiplications. I have, in fact, n multiplications. So it's going to be log x base A plus log x base a. How many times? N times. Okay, there will be n of these. Okay, so we can write it down as n log xa. And that's the rule that I've got here. If I've got a log x power n a, I can just take that exponent out. It's n log xa. Okay? We'll pause again. Okay, the next rule is, let me just see that you can see it, yeah? The next rule, I think, is the hardest one to remember and also to prove, but sometimes we do use it. It's involving change of base. So let's say I have a logarithm of a certain number base 2, but I want to write it instead of base 2, I want to change to base 10. Can I do it? And if I can, how do I do it? So let's define these things, okay? So I've got log x base b, log a base b, log x a base a. So really, what I've got is a log of x in the base a, and I want to transfer to base b. How do I do it? Okay. So what I'm going to do, I'm going to identify, or again, define this as, let's call it q, call that p, we'll call that r. Okay, we'll just give these letters. They eventually disappear anyway, as you can see at the end. So from that, we know that b to the power of q equal x, b to the power of p equal a, and a to the power of r equal x. Okay? That's this crucial rule that we move from log to exponent. Now in exponent, some things are becoming clear. Okay? If this is equal to x and that's equal to x, that means b to the power of q is equal to a to the power of r. Right? That's from those two equations. Now, b, all right. Now, a, I've got also something for a. So I can put a, instead of a, I can put b to the power of p. So I'm going to write b to the power of q, and instead of a, I'm going to write b to the power of p, and all that power r. Okay? So I just slapped in this bit into a. Okay, exponent, again, I know how to deal with that. So b to the power of q, and check, we've got the same base, so that means we're in the right track. B equal to b to the power of pr. Right, that's just, again, another rule that we haven't used it for exponent, but you know it. Same base, so what can we say? Q equal pr. And you know when you get that equation for q and p and r, we're kind of done, right? Because what is q? Q is that. So I can now go back to my logarithm. X to the base a equal log a to the base of b times log x to the power of a. Okay, so that is my rule. But I want to just write it down in kind of a sensible way. So I'm going to write it like this. Logarithm x base a. Let's say I want to write logarithm x base a. Base is a. I want to change it to base b. What this equation tells me that I can write down this logarithm x base b, right? I just shifted this down, right? So I can write down, instead of base a, I can change it to base b. See, same thing. But the price I have to pay is I need to divide by logarithm a base b. Okay, so it's a bit difficult to remember. I mean, you did get that equation anyway, but to see the sense here, I've got a base a, change it to base b, so I will write down the same with the x, but I need to divide by the logarithm of the old base with the new base. Okay, let's pause here. Okay, sorry guys, I know it's a long video, but we're almost there, okay? So the last two rules here, I think that's the last two rules, are just using that, and maybe one more thing. So I've got a log b base a, and I want to change it to base b. Okay, so I want to move from base a to base b. So I'm going to use this rule, okay? I want to move from a to base b. So I'm going to write down log base b, but what is my x in this case? It's simply b. So log b base b, ready? Okay, and here I'm going to write log a base b, just like here. So the only difference between those two is that now I have a specific x, which is b. But what do I know about log b base b? We had that here, okay? If you have the number and the base the same, the answer is 1. So here's another rule. If you have log b base a and you want to write it in terms of base b, the answer is going to be 1 log a base b. Okay? Right, next one. That is actually one that you use a lot. This one you use a lot for some reason, okay? Or I see a lot of questions like that. Let's say you have a base which is 1 over something, and you want to just write it in terms of that a, okay? So instead of 1 over base 1 over a, I want to have base a. Again, I'm going to use the same rule, okay? So I'm going to write down log x in the new base, which is a, divided by log the old base in term with a new base. Okay. Okay. So all I did is that my a here is 1 over a and the b is a. Okay. Now I'm not finished. Okay. We'll write it down. We'll write equal. Okay. Log x base a. What is this thing? Okay. Let's write it down like that. It's base a. But what is a? Okay. Or 1 over a is a to the power minus 1. Okay, right? 1 over a is a power minus 1. And now we almost there. Okay? We had a rule for an exponent. Here we go. X to the power of n, log x to the power of n, you can just check the n outside. So what my n in this case is simply minus 1. So it's going to be log x base a divided by minus, check the minus there, log a base a. Now we're going to finish it off. Okay? What is log a base a? It's 1. So I can write down finally, okay, where did I start? Log x base 1 over a will be equal to minus log x base a. That's it. Okay? Very one that you will use a lot. So I know, guys, it's quite long, and maybe I could have just given you these rules to memorize, but I think you need to understand them. I mean, even in the core maths, they give you the explanation. You don't need to prove it. I don't think in AP as well, but you know, when you understand something, it's more powerful. Okay, so that was a long video, but you don't need to practice. You'll practice in core maths. You'll do lots of exercise there. Cheerio.